Hello everyone, this is Burak Enyar. Thanks for attending our webinar today. We have a great lineup. We will be talking to members of Team 142, and this will be a case study about a CFD simulation which was run in the Autodesk cloud. My name is Burak Enyar, CEO of UberCloud. With me today I have Mark Lobo and John Den Hardog, which I will introduce in just a moment as we go into our presentation. During this presentation, if you have any questions, we will have a Q&A session at the end. I will be moderating the session. You can type your questions into the question bar, which is in the Go to Webinar control panel to your right. You can send your questions throughout the webinar. I will collect them and ask the presenters to talk about these questions all the way at the end. So our session will last about close to 1 hour today, including the questions. We will have a number of videos throughout the session. If you look at your GoToWebinar control panel in the chat section, you will be able to see these videos on the UberCloud website. We did that just to make sure that if the presentation is a little choppy on your screen, you can always switch over to YouTube and see the videos there. Okay, so we will get rolling. I would like to introduce Mark Lobo first. He is the principal engineer at Lobo Engineering PLC. Mark has 30 years of experience in industrial product engineering, and his special focus has been control valve design and application. John is a senior product line manager who focuses on Autodesk's emerging simulation products, and that would include all of the company's cloud-enabled capabilities as well. John has a background in CFD, and he previously worked in the aerospace industry. Mark and John, thanks for being on this webinar with me today. So when we look at the engineers' computing tools today, from UberCloud's perspective, we see that engineers have three options. Many engineers, well over 90%, rely on their workstations. That's where they do their design work, that's where they do their simulation work, and much of the product lifecycle is managed right on the workstation. Some companies have access to server farms. These could be these could be in their data centers, these could be in their office environments. They have clusters where they can offload some of these simulation tasks. And recently we see an emerging market of CAE cloud providers. These are professional data center providers who can provide access to powerful clusters in the cloud, remotely accessed, on demand, and basically at your fingertips when you need it, and not around when you don't want it. But when we look at each of these three options, we see that they all come with their own set of challenges. Workstations obviously have limited capacity, and they're hard, to upgrade. Every workstation resides on your desktop for a few years, and usually towards the end of that period it could be a little underpowered for the tasks that you want to run, so they tend to be a little slower. When you look at the CAE servers, which companies might have in their data centers, they tend to be a little on the complex side, obviously, because we tend to utilize complex network infrastructures. We tend to utilize special hardware, like for example GPUs, and the sticker price on many of these are quite high, and I'm not just talking about the purchase price. The entire cost of ownership is quite high. And when you look at the cloud, it's a brand new model, so a lot of people are trying to get their arms around it, and they see challenges such as security, licensing, speed of data transfers, and they simply don't know how to get over these problems. So each of these options are available, but they do come with challenges. That's why we put the UberCloud experiment together back in mid-2012. It started as a voluntary effort, and now it has well over 1,500 participants. And we have been able to put together over 150 teams, and we are talking to one of those teams today about their experience. So far, we have completed 5 rounds of these experiments, and we are always open to more projects, so that we can continue the UberCloud experiments. We put together webinars such as today's, as well as detailed documentation, which we publish as the compendium, and the second compendium appeared back in June. It has been published. If you have not seen it just yet, you can look for it in HPC Wire or Desktop Engineering. So we will now start talking to Team 142. First, I will turn to Mark, and he's going to walk us through his study. And John has a few slides which he will go through as well. So I will turn it over to Mark and John at this point.
Thank you, Brock, and thank you to all who have tuned into this webinar. Last year, Autodesk introduced Simulation CFD 360 with a trial program that coincided with my severe service valve design project. As an independent engineer working in product design and mechanical simulation, I've had little need for CFD that would justify the perceived high front-end costs. This new tool really appealed to me, and I was fortunate to have joined with Autodesk to conduct this real-world design application as a member of Team 142. So let's get into the problem. This schematic describes a simplified common installation of a control valve. Multiple parameters can be measured, fed back through a data processing algorithm to a controller that also knows the conditions upstream. The controller will then send a signal to the valve actuator, causing the valve to change its restriction to maintain a desired condition downstream. Control valves applied in fluid process systems are selected with consideration of environment, fluid composition, range of conditions, accuracy, response time, and reliability. The control system engineer is given the requirements by the process engineer, and from that develops the control valve specification. The 3 sections of this spec include physical requirements for the valve, performance ratings, and flow characteristics. The ISA standard S20.50 includes a form that can be used to summarize the spec. So how are the requirements for the control defined? First, the maximum flow capacity, or minimum restriction, is calculated to establish the valve flow coefficient, C sub V. If the pressures across the valve are known at some distance from the valve, a piping geometry factor, F sub P, must be considered. Reynolds number factor, F sub R, applies when laminar flow is expected. Liquid pressure recovery factors, F sub L and F sub LP, and liquid critical pressure ratio factor, F sub F, helps predict the pressure drop when the transition from turbulent to choked flow begins. For compressible flow, the pressure drop ratio factors X sub T and X sub TP are required to deal with choked flow sizing. And of course, ratings change with restriction throughout the valve's range of control. To measure these ratings, we use standard procedures. For valve sizing and control system modeling, the C sub V of the valve can be computed based on the system inputs and the parameter needed to be controlled. The valve can then be instructed to change its restriction to provide the required C sub V. As pressure drop increases along with velocity and dynamic pressure, the static pressure of the fluid falls and can hit the vapor pressure. The resulting phase change, followed by another as the pressure recovers in the valve body, appears as increased restriction. Above some differential pressure, the flow does not change. Choked flow. In this region, given P1 and Q, the flow rate, the predicted C sub V requirement of the valve is increased by the reciprocal of F sub L and influenced by F sub F and the fluid vapor pressure. The relationship between restriction and control position describes the valve's range of control. The system designer selects a characteristic for the valve based on the projected requirements. The designer can then input the applicable valve ratings in the control algorithm to permit rapid overdamped response in order to maintain system stability during input parameter changes and other disturbances. In this chart of flow rate versus square root of differential pressure for a typical globe-style control valve, we observe the constant relationship while flow is turbulent, the linear portion, and a rolling off of the curve during the transition to choked flow. Since the flow rate in the transition region is not predictable with the ratings for turbulent or choked flow, process control is challenging. So, the challenge for controlling in the transition region is typically avoided by limiting the pressure drop. For the typical control valve with F sub L of 0.88, pressure drop is limited to half the upstream pressure. Therefore, for severe service applications with very high pressure drop, the system designer seeks a valve with F sub L above 0.95, which defines a small transition region and a wide range of control. My objective with this project is to develop such a severe service control valve. We're designing a valve, so we have the model. And we have the tools for mechanical and heat transfer simulation. Why not run a complete suite of flow tests on a digital model of a valve? No physical model required, no test facility, just a workstation and CFD software is all that is needed. And time, since measuring the ratings of a control valve through its range of control can require 100 flow tests. We have to have several data points, with flow fully developed turbulent, plus enough data in the region where pressure drop is more than half the upstream pressure. Seamless integration between modeler and CFD software, along with quick scenario setup, would make it nice when evaluating design alternatives. Because the phase changes of the fluid will experience in the flow path challenge convergence, we need to have extensive control of solution settings. I also expect the simulation results to mirror physical test data. So what kind of time does CFD need to calculate a solution and return results? During my experience working on the UberCloud Team 142 project, I was used to an average of about an hour to run a simulation of a single scenario on my local workstation, with a combination of one control position and two parameters of the three required to calculate valve ratings: upstream pressure, downstream pressure, and flow rate. Could I tie up my workstation for days running 100 simulation? Worse, could I let them run in the background while doing other work, sapping resources, and take a month to generate the data set? The model can be configured in 10 control positions and boundary conditions in a few hours. And I was going to find out if Autodesk Simulation CFD 360 could return results in hours instead of days. At this point, John will demonstrate the workflow that is common to all problems thrown at the program. Take it away, John.
Thanks, Mark. And nowadays there are lots of different ways that you can access the cloud for simulation. And before we go ahead here, we thought it might be useful just to show you the workflow that Mark used, and we'll use a simple example to do that. So this is an electronics enclosure, different from Mark's valve, but the workflow is really going to be the same. And here we're looking at 4 different designs so we can compare. And something unique about this application is the ability to easily switch between local and cloud solving all on the fly. So here we're just specifying where we want the simulation solved. And in this case, we're just going to push all of them to the cloud and get them all solved at the same time. So what's happening now is the inputs are all being uploaded to the cloud, and normally this is pretty quick because the data is fairly lightweight. And once it's uploaded, the information is going to start to stream back just to let you know how things are proceeding. So here in the output bar down at the bottom of the screen, you see some information about the meshing and solving processes, just like you would if you were solving on your own local machine, but this is all really occurring on the cloud. And this job manager window that's shown sort of in the front is giving you feedback on how all the simulations are proceeding at the same time. So you can see that each one is in the solve phase. Now in a second we're going to start to see some intermediate results coming back. So as these are all running, you can access the data and sort of get a sense of how the solution is evolving in each case. So we'll pop over to one of them here. This happens to be the first design. And we see that the data is starting to come back. We're partway through the run, and we can look at the details. So here we're just slicing through the model. We can make sure that everything is set up properly and just understand how things are evolving. So since all this is running on the cloud, there really isn't going to be much of a burden on the local machine. So my CPU really isn't going to be used at all. So in fact, in a second here, what I'll do is I'll shut down the UI, so we can close down everything and actually disconnect if we have to. And this is really great for people who travel, because if they ever have to unplug, they lose their network access, or they get on a plane or whatever, they might not always have that connection to the cloud. But what this means is that they can continue to have those simulations solve while they're offline, just like they would hope and expect. So here I'm actually disconnecting from the cloud and then coming back on. And when you resume that connection, you just sign into the application. I'll sign in here in the Job Manager window. And we get that report of how everything is continuing to evolve, and we can just open up one of those scenarios and get back to where we were. So again, really useful for folks that are traveling, or maybe they move between different offices and they want to have the flexibility to keep solving as they move around. So when everything is done, all the data is going to be available for comparisons. So you can compare specific values like pressures or flow rates, like in Mark's case, or others like temperature and several others. And this is really the basic workflow that Mark used for the valve design project. It's like an extended desktop. So you can follow this desktop workflow and solve simulations locally if you like. But when you have a lot of runs to complete, you can push them to the cloud for this burst solving capacity whenever you need it, just straight from the exact same application. So Mark will now go into details about his project and how he ran the simulations.
Okay, great. Thanks, John. Yeah, that was very informative, and I've seen, of course, a lot of those processes through my experience. And my experience with industrial and oil patch control valves taught me to respect the amazing erosive magnitude of high-velocity fluid, laced with a little sand and a little water, that will vaporize and then implode, causing cavitation damage when it strikes a surface. And when a control valve throttles down and velocity increases, the flow stream will try to blast its way through a tungsten carbide liner and valve body. For the purpose of this experiment, I wanted an ideal flow path. The valve should have a straight body with simple inlet and outlet transitions. The restriction, or trim in control valve parlance, should cause gradual velocity changes and minimize direction changes. The low static pressure of the fluid at the exit of the trim that could cause a fluid to vaporize should be kept from recovering when fluid impinges on the flow path boundary. Remember, I was looking for a very high F sub L. The choice of actuator should allow flexibility. So the valve will need, as we get back to our slideshow, so the valve will need an internal rotary to linear drive that is efficient and does not compromise the flow path. So the optimized flow path is simple, with a sleeve that moves axially to change the annular area between the seat surface and the plug. Simple, sure, and later we'll figure out how to design a valve around it. After watching 2 online tutorials, one about setting up and running a simple CFD simulation of a valve conveniently, and the other about setting up multiple scenarios and design studies, I loaded the model. It just takes a couple of commands to identify the flow path shown here. The program is pretty amazing in that I just selected the intake and exhaust port planes, and in an instant it showed me where the fluid is. The restriction, the plug, is still there, of course, inside the fluid, which is water for this test. Following standard practice as a new user, I set the flow rate to 500 GPM, the upstream pressure at 500 PSI, entered the data requested by prompts, left alone the default settings for meshing and solution, and clicked Solve on my local workstation. The cross-section plane shows the distribution of the pressure at the fluid boundary and about 450 psi-G at the discharge. Considering that my prediction of the C sub V for the valve was 70, and this simulation predicted 70.71, these were very reasonable results. Very reasonable results. As one of my Algor trainers said during a session years ago, this shows the program isn't just a random number generator. So encouraged that turbulent flow simulations with no phase change would be accurate, I eased into choke flow by setting upstream pressure to 200 psi-G and downstream to 0. The solution setting dialog box included an option cavitation on, so I checked it knowing these conditions would cause the fluid to vaporize. The results window displays a chart of several key parameters as the program iterates the solution. Since I've asked the program to calculate the volume flow rate, the V sub X trace is of interest, and after 500 iterations did not look like it was going to settle down, and other parameters did not look like they were close to flattening out either. Again, the multitude of settings in the software was still set to default values, and I thought, let's just run another 500 simulations. As the number crunching advanced, it was pretty clear that the solution just was not going to converge. Somewhere in the enormous matrix Simulation CFD was trying to solve, there were static pressure values that were dipping below the vapor pressure of water, less than 1 psi-A. Thus, for an instant, the incompressible fluid was now a gas. Looking closely at the dithering, I could just imagine that instantaneous change of fluid velocity, fluid density, caused an overshoot that led to another change in density. My colleagues at Autodesk made it clear that Simulation CFD 2014 would have difficulty with the massive vaporization that would occur. Okay, but all I need is volume flow rate, simply the average velocity at inlet times the area of inlet. I also complained that the flow path was simple, and the boundary conditions were just the upstream pressure and downstream pressure. So what about all those options for meshing in the solution methods? Digging deep into the Autodesk reference material took me into an amount of content suitable for a graduate course in fluid dynamics. Surely there was a way to set up the model to settle down enough during the solution to at least give me data to work with. I had seen that conversion is not a problem when the fluid remains a liquid, and all I needed was the program to return enough data to tell me when the fluid vaporizes, which happens as expected in choked flow. Still running simulations locally, I threw serious severe service conditions at the model and gave the results a hard look. The complete data set for each iteration is easily extracted into a CSV file, and this chart was the result. It seemed to me that there must be a group of settings that would allow the simulation to get close to converging and stop before it starts to wander off. After posting this on my team's website, Autodesk politely suggested that I increase the number of layers of mesh at the boundaries of the flow path and make a few changes to the solution settings. Now I was ready to go to the cloud. To recap, I figure I needed 10 data points over the span of pressure drop settings for each control position. In the range of differential pressures that yielded fully developed turbulent flow, I just needed 3 or 4 data points, figuring that they would line up to represent C sub V. And the rest would be clustered in the higher pressure drop range to identify where the flow chokes. It's not easy being dramatic here, because 10 scenarios were created in a couple minutes by cloning and changing the downstream pressure value, bringing up Solution Manager and clicking Cloud for each scenario as John demonstrated. While it was entertaining to watch the convergence progress of 10 solutions running simultaneously by selecting various scenarios, as you saw, to display the convergence chart, my workstation was at idle, so I could fire up Inventor and do some useful work without straining the operating system. In this chart, I show only 2 of the control positions I modeled just for clarity. In all cases, the simulation produced data that could have been lifted from a textbook, predicting that the ideal flow path helps prevent the fluid cavitating in the valve body in choked flow, yielding little change to the observed C sub V throughout the complete range of pressure drops. While 11 control positions are ideal to fully map the characteristic, 5%, 10%, 20%, and so on, I ran just 6 design studies to find out if virtual valve testing is a viable way to verify a valve design. This was simple. Change the position of the trim in Inventor, activate SimCFD, and tell the program that this is a new design study with the same settings as another design study. All this takes just a few minutes for each control position. This chart includes the results of 2 series of simulation covering much of the control range. In general, C sub V measurement should follow the increase in annular area and at the restriction in an expected way as the valve opens. Also, as long as flow is fully developed turbulent, the measured inherent characteristic is independent of pressure regime. The 3 data points from the series with low downstream pressure reflect influence of a prominent laminar flow boundary layer, effectively restricting flow, lowering the measured C sub V in the test. All the data that was turned from the cloud looked good, almost eerily good, since I've seen physical test data exhibit similar patterns, and was exactly what I expected to see from a true simulation. One thing that was missing was a real-world phenomenon called data scatter, until I looked closer. As I've seen many times with physical testing, data in the choke flow region is not very stable. Why? Simply due to the randomness and chaos of the phase changes going on in the valve body. Instrumentation has difficulty in settling down. I adhere to the policy, if you can't take good data, take plenty of it and work with statistics on the data scatter. My colleagues at Autodesk may cringe at this, but I couldn't help make the comparison to physical testing, since convergence in the simulation might stop at a high or low spot when the convergence criteria are met, thus exhibiting a tiny bit of data scatter when the simulation is repeated or boundary conditions change slightly. As expected, the measured C sub V fell as the pressure drop approached the upstream pressure, indicating vaporization was taking place. The data smoothed to fit nicely with a curve that indicated this was a model with a very low recovery valve, again as I expected, with F sub L of 0.97. There are many ways to view results in SimCFD, but this simple cross-section offers us a lot of information about the flow path. The abrupt changes in velocity magnitude that is observed will influence changes to the plug to smooth out the rise in velocity as the fluid approaches the restriction. Better management of velocity through the valve will reduce internal damage and vibration-induced noise. The flow path can be studied as the valve moves through its range of control. And when the flow path is tweaked, new design studies can be simulated rapidly in the background so that the design engineer can keep his workstation working on product design that the boss needs yesterday. So to recap, local solves were performed on an HP Z800 and could take as long as 3 to 4 hours when the machine was busy working on stuff. The cloud solves were run at one of the Autodesk HPC centers, with results from 10 scenarios returned in under 3 hours. With order of magnitude savings recorded and even greater savings hinted as procedures for virtual valve testing are refined, SimCFD has proven to be a valuable tool in this design engineer's toolbox. Back to you, John.
All right, thanks, Mark. Yeah, it's been really fun working with you on this project, and I thought I'd share a bit about our general approach and why we developed these products the way that we did. So first, Autodesk has a really broad reach in many different disciplines of engineering, and a large part of our mission is to help everyone, not just big companies with deep pockets, make great products and great designs. So we've made a big investment in simulation over roughly the past 10 years and brought in a variety of different kinds of technologies to help our customers do the kind of virtual testing that Mark did. So today these capabilities include a variety of mechanical stress and FEA capabilities, there's fatigue analysis, composites, energy analysis, CFD, thermal, molding simulation, and other types of advanced manufacturing. So a pretty broad array of different types of capabilities. Next slide, Barack. And so what we've observed are really 3 main trends that are related to this idea of cloud computing. And the first one is that customers are setting up models that tend to be bigger than before and more complex than before. So the models tend to take more time and resources to solve. And then secondly, they're increasingly looking at many simulations, not just one, so that they can test different design ideas and different operating conditions, again, like we saw here in Mark's project. And then third, because nowadays most tools allow you to quickly set up multiple runs, after customers set up that initial model, the main bottleneck that they face is really solving and having the resources and licenses available to do that solving. So when we go out and speak with our customers about the cloud, we see that there are a lot of different reactions. Some just simply can't use it due to policies, but this is a pretty small group. And at the other end of the spectrum, some say that they're all in. They're all about moving their workflow to the cloud. We think this category is going to grow a lot in the future if you know what we see happening with online banking and photos and other services are any indication. But today it's fairly small in the engineering world because the most common design tools really live on the desktop still. So right now the biggest category we see is folks in the middle, the ones that have existing tools and workflows that they need to integrate with, but at the same time these folks are also pretty open to using the cloud when and where it makes sense. So our philosophy with these projects really involves 3 different things. The first one is to get around those solving bottlenecks that we see a lot of. Some of our customers have a lot of simulation licenses in their own private compute clusters, but most of them don't. And we want to give people access to computing power and licenses when they need it. The second one is that we want to make it easy to go from your own machine to solving in the cloud. So people are using desktop-based CAD tools, and they often want to test out different variations on a simulation when first getting started. So we want to make it easy for you to work locally and then just call on the cloud when and where you need it. And then the third one is we want to make access really simple and predictable. So our plans for these products give you access for a fixed amount of time. You can travel wherever you want and use it as much as you want locally. And then whenever you solve in the cloud, there's just a flat rate for each simulation. And like a phone plan, we give you a certain amount included as part of your plan. And if you need more than that, you can always buy more as you need it. So overall, you can use this product just to solve locally, much like you would with a traditional product. And when you have more that you need to get done in a short amount of time, you can switch to the cloud. And then you can run multiple simulations at once. And when you do that, you're basically just sending up the inputs for the mesher and solver to the cloud. And once it's completed, all the data is going to come back to your system and reside on your desktop, just as if you had solved it locally, but you've been able to leverage the cloud to actually do the computing. So today we looked a lot at CFD, which has been showing really great adoption just due to the relatively compute-intensive nature of CFD models. You can go to the next slide, Barack. But similar workflows are going to be available for other areas like large-scale building structural analysis, linear, nonlinear FEA and mechanical event simulation, and plastic injection molding simulation using Moldflow Insight. So the cloud versions of these products have been around since 2012, and we've been working with customers and partners like Mark to understand the needs that are out there. And it's been really exciting to see more and more people being able to take advantage of the compute power that the cloud provides. So yeah, going forward, we look forward to working with others in beginning to apply these workflows to the problems that they're trying to tackle. Thanks.
Mark, John, that was really impressive. Thanks for all the information you have provided. I see that a few questions are already rolling in, and if you have a question, you can always put it into the question bar on the GoToWebinar control panel. It should be to your right. I'll throw the first question that I see here to Mark. You stated there's an order of magnitude in time savings. What is the net result of such an improvement in performance?
Well, let me first say that estimate was very, very conservative. Many of the simulations I ran that, as I said, took about an hour or 3 or 4 hours when I was actually using the workstation for something else, and causing it to time slice. Many of those didn't even converge. I mean, they would give me this data scatter that I made reference to. Since we put this together and the more I worked with this, I've seen simulations run locally that may take 8 or 10 hours. And if you start putting an order of magnitude on top of that, then you can do in working in the cloud, you can work in one day versus, like, say, a month worth of time if you just let the simulation run. So again, it's kind of qualitative, but the power of it is when you can pull up the solution manager, and it's like having a room full of computers, and that's really the key thing, particularly in this type of project where I had to take 100 data points to really prove out a valve design.
I have one more question that you could tackle here, Mark. Was the interactive visualization done on the cloud or on your workstation?
The visualization was all done locally. This is just processing this, if you will, massive amount of data that is returned when the cloud finishes its calculating. So once it's back on the local workstation, you can use many of the controls, the visualization, the planes that John demonstrated passing through the model. Particularly in my valve design, there were very precise details that I could zoom in on and see how the flow was really affecting. And actually beyond that, using integrating this with simulation mechanical, you can look at the reaction loads and forces actually on the pressure boundary. So all that's done locally, and it's the type of thing where if your machine's pretty quick, you can just do it all in real time locally.
Thanks. And John, can you confirm the CFD solver that's being used behind the service is the CF Design product, or is it the Algor CFD?
It's an evolution of the CF Design product that was acquired from Blue Ridge Numerics back in 2011.
That's great, thank you. And can you also talk about the licensing a little bit? If you have a Simulation CFD license already, how do you use the Autodesk products on the cloud service?
So there are two different ways that we make it available. There's a perpetual product that we sell. So if you have that perpetual product, that's something that you own, and you can use it within your firewall. The service is something separate. So you would purchase access separately. You would have a named user that could use it wherever they move. It's not going to be locked down to a particular site, but it is handled separately. It includes service and support and updates along the way. So it's just one fee that you pay per year, as opposed to a perpetual offering where you buy it up front and then there's a maintenance fee that goes along with it for updates.
Right. And can you share with us how many nodes and cores per node are being used for each of these CFD jobs? Yeah,
so first I'd say it varies by the type of product and application, and it's always changing. It's because the resources on the cloud are constantly being updated. So for this particular case, I think Mark had in his slides, it was each run was going to get 8 cores and up to 64 gigabytes of RAM. So when you're solving several at once, you can imagine it's a fairly large number of resources available.
Right. So on the client side, what are the resource requirements? If the solver is running 100% in the cloud, could you then utilize a processor that's relatively low end?
Yes, the CPU requirements locally are fairly minimal. It's not really critical that you have a large number of cores locally. You might want a fair bit of RAM, especially for doing really advanced visualization and post-processing. But the CPU requirements locally are relatively low.
And can you address the needs for a GPU card at the client end?
Right now, we haven't seen many benefits through GPUs. It's something that we continue to monitor and explore the potential around. But right now, there's no need to have an advanced GPU available.
Great. I'm going to return to licensing for just a moment here, John. We understand that the licensing model currently is annual, correct? Are you looking for opportunities to reduce that to shorter periods of time?
Yeah, that's a good question. It's something that we've explored with several other products. Right now, it is available annually. I can't say there are any specific plans to offer anything shorter than that in the near term, but as needs come up and our customer base asks for it, we'll explore it. But right now, up to this point, we haven't seen much demand for very, very short duration access.
Mm-hmm. Okay, let me turn back to Mark on this question here. It's coming from Doug. Doug says, how does time versus mesh size scale function in this application? Did you have some experience around that?
Well, yes. Again, it's hard to be quantitative here, but there is a considerable increase, again, using like default settings. I think the default is 3 layers of mesh at the boundary walls of the fluid for this, the high velocities I was dealing with, and this phase change issue due to vaporization, it was suggested by Autodesk to increase that wall thickness to 8. That would drive up solution time. It would also increase accuracy. So again, my experience is pretty small with this, with Simulation CFD. As anyone involved in simulation probably can understand, it's good to take notes while you're setting up problems and running time checks and looking at the data, because there's so many capabilities. I mean, an endless amount of capabilities with the software to concentrate mesh and so forth. And by the way, the program has great diagnostics. You can let it diagnose your mesh instruction, and it will tell you where you might have problems to concentrate. So again, that order of magnitude time savings versus running things local was very conservative. I mean, it could be considerably more than that.
Thank you. So I have a question here about security. The question simply is, how is the security handled in transferring data? I want to make a quick comment about UberCloud experiment and how we see security, and then I will turn it over to John. In the scope of UberCloud experiments, since we work as a pretty wide-ranging team, we request our end users to not use a model which has a high level of security requirement. So we all understand that security can be layered on top if we do have, the experiment results show that the application is worthwhile using in the cloud. So with that brief note, I'm going to turn it over to John. In general, John, what are the security capabilities of this product?
Sure. So I guess I'll just describe what data transfer happens. On both the upload and the download, everything is first going to be encrypted using SSL. And furthermore, it's going to be chunked into different pieces. So it's not just one file that goes from your machine to the cloud and back. It's going to be broken up into different pieces that need to be brought together. And again, all those pieces are encrypted. And furthermore, the format of the data is something that is specific to the simulation application. So the overall level of security is it's at a level that's similar to what's commonly used in the banking industry, and then furthermore, the actual data itself would be very difficult to reassemble if it were ever intercepted and unencrypted.
Great. And John, since I have you, I'll ask one more question. Could you currently or in the future do the visualization in the cloud? Say you're traveling and you want to access the solution on an iPad or a low-end computer. Is that something you're capable of doing today with the service, or is that something you would consider in the future?
Yeah, with this one, we have the ability to save a completed result set on our essentially our cloud file server, which is just called Autodesk 360. You can take the CFD result set, upload it there, and then it becomes viewable in just a standard web browser. You can look at the results and query the model that way. We have other products that allow a deeper level of integration with just cloud viewing, so you could actually create new types of visualizations all in a cloud-based environment. But with this product, it's mainly about viewing. You would still set up the initial result set locally.
Excellent. And John, I think we will be going kind of backwards. I know you covered this already, but I'm receiving numerous questions about how the licensing works, especially around its pricing, not necessarily in dollars, but is it by the hour, is it by the minute, is it by an annual license? So could you cover that one more time, please?
You pay one fee for annual access. So when you purchase that annual access, you can use it locally as much as you want, and we actually give you a couple different tools. There's CFD capabilities. There's also FEA and structural analysis capabilities all included. So that's the upfront cost. It also includes credits for solving in the cloud. So when you do want to solve in the cloud, there's a flat rate that's charged for each simulation. So when you first make the purchase, you have 1,800 cloud credits. For each CFD run that you solve, it's going to deduct 15. So essentially, with that initial purchase for access for a year, included within that is the ability to solve effectively 120 CFD simulations. If you need to go beyond that, we sell these individual cloud packs if you want to continue solving in the cloud. But again, you can do as much as you want locally.
And still related to that, can you change the number of cores that your simulation is running on? You know, take it from 8 to 32 to 64 to 256, etc. I mean, do you have flexibility around how much resource goes to your simulation?
Yeah, I understand. That's something that not a whole lot of folks have asked for. So right now, no, that's not the case. But you know, if there are emerging needs in that area, it's something that we'll look at.
Great. In terms of the solver underneath, John, can you comment on how much development went into it? You know, say since 2011. How much faster do you think this product currently is?
Sure. So first of all, I'd say that through the acquisition, you know, the Blue Ridge team that originally developed the solver was maintained. So a lot of our developers are still on staff and working on the product. So we've continued to evolve it with the benefit of having all the knowledge and expertise of that original team. And we've continued to see improvements on speed. So for certain classes of problems, the improvements have been dramatic. So for example, radiation problems can be up to 30 times faster just due to some of the algorithms that we improved in that area. For a flow application like the one that we looked at here, the improvements are not quite 30 times faster than they used to be in 2011, but still, I think just this past year we had about a 10 to 15% improvement. So we've been incrementally realizing gains along the way, and particular areas within certain types of physics, we've seen pretty dramatic gains.
Well, excellent. And Mark, John, I still have a few questions remaining, but we're getting short on time, so I will proceed. So if you would like more information about Team 142, I'm currently displaying the URL for further information. You can always go to the UberCloud Compendium of Case Studies and download it. It has Team 142 and about 15 others included there. You can always point your browser to the Autodesk exhibit on UberCloud. And if you would like to you know, get your hands dirty, you can always go to the UberCloud website and join an UberCloud experiment team, and that's the way to get more information on your specific use case. So I want to thank all of you for joining the webinar today, and very special thanks to both Mark and John for presenting this wonderful presentation. Thank you so much, guys.
You're welcome.
Thanks.
All right. Thank you, everyone. Have a great day.